Hi there. The title of my poster is The Variational Framework for Phase Field Modeling of Fracture in General Dissipative Solids. This work is done by a collaboration between Duke University and the Sandia National Labs. So in this work, we extend the state-of-the-art variational approach to fracture to incorporate more coupled field phenomena such as inelastic deformation, associated flow rules, as well as viscous regularization and thermal effects. So here is a very brief summary of the theory. If you are interested, feel free to refer to these two references. Okay, so the basic idea of the framework is fairly straightforward. We start from the first law of thermodynamics. We construct this potential L, and we state that the thermodynamic conservations and balance laws follow from these variational statements. Okay. Also note that the flow rule as well as the yield surface also follow from the joint minimization problem included in this variational statement with respect to the rate of the plastic deformation gradient and rate of the equivalent plastic strain. We introduced this concept of external and equilibrium temperatures to account for heat generation due to dissipations. And you can also see that the second law of thermodynamics will require the Duke kinetic potentials to be convex. We also introduced this Taylor-Craney factor Q and the coalescence dissipation to divide the fracture and the plasticity processes into energetics and dissipations. Okay, we are able to construct several models following this framework. So first of all, we are able to show that with some special choices or with careful choices of some constitutive assumptions, we're able to obtain some favorable constitutive responses. For example, here we are able to obtain an unperturbed elastic plastic response prior to the onset of fracture, and also a regularization length independent critical fracture strength. We are able to show that the crack resistance curves that we obtain from a surfing boundary value problem with stable crack propagation is regularization length independent. We're able to construct some very useful models to tackle these challenging benchmark problems. This is a simulation of a three-point banding experiment, and this is the Sandia fracture challenge. As you can see here, both in terms of the crack path and in terms of the load displacement curves, our simulation and the experimental data have an excellent agreement. Given the fact that these problems are challenging, I think this is phenomenal. We are also able to demonstrate the flexibility of the model by extending the framework to account for other coupled fields. For example, here we're able to model oxide spallation in high temperature heat exchangers. So this is a fairly complicated problem with quite a few coupled fields. So if you're interested, feel free to stop by and we can discuss further. And this is pretty much all I have here. Thank you.